In activity 3.9, we are taking some piece of cardboard that is initially 10 by 15, and we're cutting out the corners to fold it up and turn it into a box. So we'd fold along these dotted lines. So first thing we need to do is state some kind of unknown. So I'm going to use x to be the length of the cutout, because that's going to allow me to label my diagram. So all these little cutouts end up being x. Now notice when this folded up, x is also the height of the box. And the problem said the box needs to be at least an inch deep and no more than 3 inches deep. So I now have a closed interval for x. It needs to be in between 1 and 3. Now from this, we can get a formula for the volume of the box. Because it's going to be the length of the box. Well, if the whole thing is 15, then from here to here is going to be 15 minus x, or 15 minus 2x. The width of the box, similarly, is going to be 10 minus 2x. And the height of the box, as we said before, is going to be x. Now this needs to be multiplied out, and just to save time, it comes out to be 4x cubed minus 50x squared plus 150x. Because I think this is going to be a little bit easier when I go to deal with the derivative. Because next thing I want to do is determine the domain of v. Well, our domain is that x has to be in between 1 and 3. Are there any additional restrictions for this problem? Well, notice if x is any larger than 5, this term here is going to be negative, which doesn't make any sense in the problem. So if we weren't given that x had to be between 1 and 3, we'd know x would have to be in between 1 and 5. Those are just natural constraints of the problem. So let's find all the critical values of this guy. So v prime is going to be 12x squared minus 100x plus 150, and we're going to set that equal to 0. Now our critical points are not going to be nice. This thing doesn't factor, so we might use something like the quadratic formula. 100 plus or minus the square root of 100 squared minus 4 times 12 times 150 all over 2 times 12. And this is going to give us two critical values. I'm going to give them as decimals. We get a roughly about 1.96187 and 6.37145. Now we're only concerned with one of these critical values because only one of them is in our interval. In fact, this one we would have used anyways even if we weren't given this restriction, because it would make a negative width unless we wouldn't have a box. So this is really the only critical value that we're concerned with. So we're going to evaluate v at our endpoints to figure out what the maximum and minimum volumes must be. So at x equals 1, the volume is 104 cubic inches. At x equals 3, the volume is 108 cubic inches. At x approximately 1.96187, the volume is approximately 132.04 cubic inches. There is our absolute max, or the largest box we can build with this piece of cardboard given these restrictions. The smallest we could build is if we let our cutout be a length of 1. So we could apply the extreme value theorem here because we were on a closed interval and we had a continuous function on that interval.